Today, we're going straight into some core engineering concepts, stuff you shared that really underpins so much.
That's right. We're talking temperature, thermal energy, heat transfer, the basics. But maybe not so basic when you really look closely.
Yeah, we want to unpack the science behind how heat actually moves, maybe touch on the history of how we measure it, which is kind of surprising.
And really show why these ideas are just critical. For engineering, obviously, but even just for everyday comfort.
Right. And the sources you pulled, they start with some pretty intense examples, like molten steel.
Yeah, pouring molten steel into ingot molds. We're talking temperatures routinely over 1,300 degrees Celsius.
Wow. Okay, so that really sets the scale. This isn't just about, whether you need a jacket.
Not at all. Engineers deal with these extremes where materials are pushed to their absolute limits. It's serious stuff.
And you frame temperature itself as, what was it, a fundamental dimension?
Exactly. Physics talks about 7 base dimensions to describe the world length, mass, time. Temperature is one of them, usually shown as theta.
Huh. One of the fundamental 7. Why, though? Isn't temperature just about how fast molecules are moving? Kinetic energy? Seems like you could derive it from mass, length, time.
That's a really good point, and physicists debate the nuances. But operationally, treating temperature as its own fundamental dimension just makes the math and the models for heat transfer thermodynamics. It makes it all much cleaner, more direct.
Easier to handle.
Yeah. It lets us ask practical questions and get reliable answers, like how hot is that computer chip going to get? Or, how much heat does a simple 100-watt light bulb actually give off? Okay.
So let's unpack that fundamental concept then, before we slap a number on it, Celsius or Fahrenheit or whatever. What is temperature at the tiny molecular level?
Right. At its heart, temperature is measuring molecular chaos. It's the macroscopic reflection of all the microscopic wiggling and jiggling.
Wiggling and jiggling.
Yeah. Think of a popcorn popper. That's the classic analogy. The kernels are your molecules. At low temps, they just sit there, maybe vibrate a tiny bit, add heat, add energy, and they start bouncing around, spinning, colliding faster and faster, more intense.
That's till they pop.
Exactly. Temperature is the single number we assign to measure the average intensity of all that frantic microscopic action.
That makes the kinetic energy link really clear.
Yeah.
But, for centuries, we didn't know about molecules bouncing around. How did people measure heat back then? Just touch.
Pretty much. Touch or sight. The sources mention blacksmiths. They were the early experts. They had to be.
Right.
They judged the temperature of iron just by its color. Dark blood red meant around 990 degrees Fahrenheit.
Wow.
Blinding white was over 2,200 Fahrenheit.
Wow.
Blinding white was over 2,200 Fahrenheit. So then we got scales. Celsius, Fahrenheit.
Right. Standardized scales. But we have to remember, they're arbitrary.
So Celsius just picked the freezing point of water as 0 and the boiling point is 100. Fahrenheit picked 32 and 212 for the same points. Just convenient reference points, really. Conventions.
Okay, so useful for everyday life, maybe, but not rooted in the fundamental physics of molecular jiggling.
Precisely. That's why engineers and scientists often need absolute scales. Kelvin and Rankine.
Ah, yes. Kelvin and Rankine, where do they come from?
They're defined by the physics, specifically the behavior of an ideal gas. If you plot how the pressure of a gas changes with temperature and then extrapolate that line downwards, it's 0 pressure at a specific theoretical minimum temperature. That point is absolute 0. The coldest anything can possibly get in theory. 0 molecular motion.
0 jiggling.
0 jiggling. Kelvin uses Celsius-sized degrees, but starts at absolute 0. Rankine uses Fahrenheit-sized degrees, also starting at absolute 0.
Okay, this leads to something really important you highlighted from the sources, especially for engineers dealing with, stress from temperature changes.
Yes, the aha moment.
It's about the difference in temperature.
Exactly. Converting absolute temps involves big offsets, like adding 273 to go from Celsius to Kelvin. But if you're calculating a change in temperature delta T, those offsets just cancel out. So a 1 degree change in Celsius is a 1 Kelvin change, same size step. And a 1 degree Fahrenheit change is a 1 Rankine change.
That simplifies things a lot when you're looking at how much something expands or contracts.
Immensely. It's the difference that drives the physics of heat transfer and thermal stress.
Okay, so we've defined temperature now. Heat. People use these terms interchangeably all the time. What's the actual difference?
Oh yeah, this is a huge point of confusion. Temperature is the state in, the level of molecular activity. Heat, or more precisely, thermal energy transfer, is the movement of energy. It's energy flowing from a hotter place to a colder place. And crucially, it only happens if there's a temperature difference.
No difference, no flow.
No net flow. That's the rule. Heat is energy in transit because of a temperature difference.
Got it. And we measure that energy flow in specific units.
Yep. The standard SI unit is the joule, but you also see the B2, the British thermal unit.
Right, the energy to heat 1 pound of water by 1 degree F.
Correct. And the calorie, based on grams of water and degrees C. And fun fact, the calories you see on food labels, those are actually kilocalories, 1,000 of the scientific calories.
Always wondered about that capital C. Okay, so energy moves. How? The sources lay out 3 main ways, right?
The big 3: conduction, convection, and radiation.
Let's start with conduction. Seems like the most straightforward.
It often is. Conduction is heat moving through something stationary. Think of that metal spoon in hot soup again.
The handle gets hot even though it's not in the soup.
Exactly. The energetic molecules in the hot end bump into their neighbors, passing the energy along molecule by molecule like a bucket brigade right up the handle.
And there's a law for this. Fourier's law.
That's the one. It basically says the rate of heat flow depends on the material's ability to conduct heat, its thermal conductivity, K, and the area, and how steep the temperature difference is. But it's inversely proportional to how thick the material is.
Okay, thicker material, less heat flow. Makes sense. And this K value, the conductivity, it varies a lot.
Hugely. Solids, especially metals, are generally great conductors, high K. Liquids are okay, much lower than solids. And gases are really poor conductors, very low K.
Why the difference? Back to the molecules.
Back to the molecules. In a solid, they're packed tight, easy to bump neighbors. In a gas, they're miles apart, relatively speaking. They might be moving fast, but they rarely collide to pass the energy efficiently via conduction.
Which is why trapped air is such a good insulator.
Precisely. This brings us to thermal resistance, the R value you see on insulation.
Right. How is R value actually defined?
It's simply the thickness of the material divided by its thermal conductivity, L over K. High R value means good insulation.
And you mentioned an analogy to electricity.
Yeah, it's really helpful. Think of Ohm's law. Voltage, current x resistance. For heat, temperature difference like voltage equals heat flow like current times thermal resistance, R value.
Okay. So R value resists the flow of heat, just like electrical resistance resists the flow of current.
Exactly. And that double pane window example is perfect. The glass has some R value, sure, but the real magic is the trapped air, or sometimes another gas, between the panes. Air has a terrible K, a very low conductivity.
Which means it has a high R value for that thin layer.
A very high R value compared to solid glass of the same thickness. That air gap is doing most of the insulating work.
Okay, so that's conduction heat moving through static stuff. What about when the stuff itself moves? That's convection.
That's convection. Heat transfer involving a moving fluid, a liquid or gas. The fluid touches a hot surface, heats up, moves away, and carries that thermal energy with it.
And there are 2 types.
Right. Forced convection is when something external makes the fluid move, like a fan blowing air or a pump circulating water. Free or natural convection happens because of density changes. Hot air is less dense, so it naturally rises away from a hot surface, replaced by cooler, denser air. Think of steam rising from a hot pie.
No fan needed there. And this is governed by Newton's law of cooling, which brings in a different factor, H.
Yes, the heat transfer coefficient, H. And it's crucial to distinguish H from K.
Okay, how are they different?
K, conductivity, is an intrinsic property of the material itself, how well heat moves through it. H, heat transfer coefficient, is about the interface between the surface and the moving fluid. It describes how effectively heat jumps from the surface into the moving fluid.
So H depends on the fluid, how fast it's moving, the surface shape, lots of things.
Exactly. It's not just a material property, it's a system property.
And the practical effect of a high H value can be really dramatic, right?
Absolutely. Think about jumping into 70-degree Fahrenheit water versus standing in 70-degree air.
Oh yeah, the water feels way colder. Freezing, almost.
Right. Same temperature, totally different feeling. Why? Water. Water has a much, much higher H value than air. It strips heat away from your body via convection incredibly efficiently. Air is much gentler.
Makes perfect sense. Okay, third mode, radiation. This one's different again. No medium required.
None at all. This is energy traveling as electromagnetic waves, specifically thermal radiation. Everything with a temperature above absolute zero emits it.
Like heat from the sun traveling through the vacuum of space to reach us.
The perfect example. And the key thing here from the Stefan Boltzmann law is that the amount of energy radiated is proportional to the absolute surface temperature raised to the 4th power. T to the power of 4.
4th power. Okay, that sounds significant.
It's huge. It means if you double the absolute temperature of something, it radiates 16 times more energy. A small increase in temperature leads to a massive jump in radiated heat.
Wow. So for really hot things, furnaces, engines, stars, radiation becomes incredibly dominant.
Extremely dominant. It's why managing heat in high-temperature systems, like spacecraft reentry shields or fusion reactors, is so challenging. The T to the fourth relationship is unforgiving.
Okay, let's pivot a bit and apply these ideas. How does this stuff show up in engineering design, like in buildings or structures?
Yeah.
First up, specific heat.
Right, specific heat. This isn't about how fast heat moves, like conductivity, but how much energy a material can soak up before its temperature actually increases.
Its capacity for heat.
Exactly. It's the energy needed to raise 1 unit of mass by 1 degree. Water has a famously high specific heat, around 4,180 joules per kilogram per Kelvin.
Okay. And compare that to something else, like concrete.
Concrete is way lower, maybe around 880 J/kg.
So put the same amount of heat energy into a kilo of water and a kilo of concrete.
The concrete's temperature will shoot up much faster and much higher. Water resists temperature changes because it can absorb a lot of energy for each degree rise. It has high thermal inertia.
Which is why coastal areas have more moderate climates than inland areas. The ocean acts like a giant thermal buffer.
Precisely. And this difference in how materials respond to heat leads directly to another big engineering problem: thermal expansion.
Things getting bigger when hot, smaller when cold. Civil engineers deal with this all the time, right?
Constantly. Especially with materials like steel and concrete and bridges, roads, railway lines.
Yeah.
Things that experience wide temperature swings.
You need to account for that movement.
You absolutely have to. Using the coefficient of linear thermal expansion, alpha. If you don't design an expansion joints or other ways to accommodate the material growing and shrinking,
It'll buckle or crack.
it'll tear itself apart under the stress. Those gaps you see in bridges aren't mistakes. They're essential thermal engineering.
Okay, let's bring it down to the human level. HVAC systems, heating, ventilation, air conditioning. Engineers are designing for our comfort. What goes into that calculation?
It's complex, but the big factors are the surrounding environment, air temp, humidity, air movement, and critically what the person is doing, their activity level.
Activity level, how do you quantify that?
We use the metabolic rate, measured in MET units. 1 MET is the energy your body produces just sitting quietly.
Okay, baseline.
Right. But if you start walking, typing, exercising, your MET rate goes up. Competitive wrestling, the sources mentioned, can be up to like 8.7 MET.
Whoa. So nearly 9 times the heat output of just sitting there. The HVAC system needs to handle that extra heat load.
Exactly. More people, or more active people, means the system needs more cooling capacity.
And what about clothing? That must play a huge role.
A major role. We measure the insulating value of clothing using Clo units.
Glow units.
Yep. It's a bit of a weird unit definition.
Yeah.
0.88 degrees F tier to HB2, if you must know.
Okay.
But basically, 1 Clo is roughly the insulation provided by a typical business suit.
Okay.
So wearing shorts and a t-shirt might be 0.3 Clo, while a heavy winter coat could be 1.5 Clos or more. Engineers use expected Clo values, along with activity levels and desired room temperature, to calculate heating and cooling needs.
Fascinating. Okay, nearly there. 2 more quick concepts. Fuel heating value.
Simple idea. How much energy do you get when you burn a certain amount of fuel? Like joules per kilogram or betas per gallon.
But there's a nuance. Higher versus lower value.
Right. When you burn fuel, you often produce water vapor. If that vapor condenses back into liquid water within your system, it releases extra heat, latent heat. The higher heating value, HHV, includes that extra heat. The lower heating value, LHV, assumes the water stays as vapor and leaves.
So LHV is usually more realistic for calculating the useful output of, say, an engine or a furnace where the exhaust is hot.
Often, yes. The distinction matters for accurate efficiency calculations.
Got it. Last one. Degree days. Sounds like a weather thing.
It is, but it's an engineering shortcut for estimating energy use, mainly for heating buildings over a whole season or year.
How does it work?
You pick a baseline temperature, often 65 degrees Fahrenheit in the US. For each day, you find the average outdoor temperature. If it's below the baseline, the difference is the number of heating degree days for that day. If the average outside temp was 50 degrees AF, that's 65 minus 50 equals 15 degree days for heating. If it was 70 degree AF, it's 0 heating degree days.
And you just add these up over the year.
You add them up. The total annual degree days for a location gives you a really good, quick estimate of how much heating energy a typical building there would need. It connects long-term weather patterns directly to likely energy consumption.
A simple proxy for a complex calculation. Clever.
Very practical for long-term planning and comparisons.
Wow. Okay, we've covered a lot. From molecules jiggling around to these fundamental laws, Fourier's, Newton's, Stefan Boltzmann governing how that energy moves.
Right, through conduction's molecular bumps, convection's fluid flows, and radiation's electromagnetic waves.
And we've seen how engineers use these ideas, thermal conductivity, R values, specific heat, expansion coefficients, even MET and CLO units to design everything from windows to bridges to HVAC systems.
It really bridges the microscopic world of particle motion with the macroscopic world of buildings, machines, and human comfort.
So, to wrap up, we talked about absolute zero, that theoretical floor, the coldest possible temperature.
The point where all classical molecular motion stops. A fundamental limit at the bottom.
But what about the other end? Is there an absolute hot?
That's the fascinating contrast, isn't it? Based on current physics, while we have that absolute minimum temperature, there seems to be no theoretical upper limit to how hot something can get.
Really? No ceiling?
Not that we know of. We can imagine temperatures far beyond the core of stars, approaching conditions near the Big Bang. There's no known physical law imposing a maximum temperature like there is for a minimum.
A hard floor at absolute zero, but an apparently infinite ceiling. That's quite something to think about.
It really is. It frames the whole concept of temperature in a pretty profound way, doesn't it? The boundaries, or maybe the lack thereof.